So it's an onto map. It's also one-to-one. This is a bijection. Like I said, I would personally not come up with this by myself. Like full disclosure, this is something I found on the Math Stack Exchange, and a fellow named I'll probably mispronounce his name. Oh man, where'd it go? Rats. There it is. SF, or Asaf perhaps, Karag. Yeah. This guy writes a lot of answers and like hard set theoretic stuff. Anyway, credit where credit's due, not me. But I think if you understand this example, you can manipulate it to solve the homework problem, which is similar, right? Like let's think about this together for a second. What if you wanted to come up with a bijection instead of this? Like hypothetically, example 8.3.6 tilde, right? Suppose you wanted to come up with G, a mapping from 0, 1 not included to 0, 1. What would you do if you wanted to come up with a bijection from this half open, half closed interval? Yeah.
You could remove the second part of the f of x that you have written.
Okay, so you're like just
remove that
just
second line.
just cross this out.
And change the third line to 1 over 2 to the n plus 1.
Fair. Yeah, I think you're right. I think that would do it. Same idea. It's just now we only have one endpoint to deal with, and then the rest of the sequence we just have to shift by 1 rather than 2. Right? Once you really understand this construction, you could do many similar things. It's a trick. Yeah. I'm sorry, it's not a trick, it's a technique. If we have a trick that we that we respect, we call it a technique. But anyway. Okay, so moving along here. That brings us to Cantor's theorem. So to me, the most interesting part of that video was the fact that Cantor was a Lutheran. I had no idea. But anyway. Makes a lot of sense, actually. Lutherans can be very hard-headed. Some of the most hilarious arguments on the internet right now are due to Lutherans. All right, so here we go. Definition. The cardinality of A is equal to the cardinality of B. I guess I've been using this implicitly already, right? If and only if. Fortunately, I've been consistent with the definition I never gave you. If and only if A is equivalent to B. All right? Otherwise, the cardinalities are not equal. So what I'm defining right here, guys, is what's called transfinite arithmetic. The number of A is less than or equal to the number of B if and only if there exists an injection F from A to B. All right? And so that's 1, 2, 3. The cardinality of A is strictly less than the cardinality of B if and only if the cardinality of A is less than or equal to the cardinality of B and the cardinality of A is not equal to the cardinality of B. Anybody care to restate number 3 in terms of maps? Because this is a statement about mappings. Don't be fooled. What is this saying? What does this mean?
There is an injection, but there is not a bijection.
Very good. there is an injection f from A to B. However, there does not exist a surjection. All right. Well, maybe that's not quite right. I mean, there doesn't exist a bijection, right? There doesn't exist a mapping which is simultaneously an injection and a surjection. Maybe I need to have F on both of these. I don't know. I have to think about that. I'm not going to figure that out in class. But certainly there does not exist a, I can certainly word it and say there is an existence, however, it cannot also be surjective. This much for sure is true, okay? There we go. I have a suspicion that may also mean that there just doesn't exist a surjection, period, but I should check on that. All right, so these define what you might call transfinite arithmetic. Cantor's theorem, another one of Cantor's theorems here, is the following. Recall for a set S, we have P of S is equal to what? U, a subset of S, right? Well, U, such that U is a subset of S, right? The power set, it's the set of all subsets, right? You guys remember this? We talked about power sets before. Yeah. Well, Cantor's theorem simply says that the cardinality of a set, all right, is strictly less than the cardinality of the power set of S. This is like obvious for finite sets, right? We looked at this explicitly for finite sets before, right? You guys remember how that went? What was the cardinality? Let me remind you, if S finite and the number of things in S, which is the cardinality, is equal to n, then the cardinality of the power set of S was what?
2 to the n.
2 to the n. Very good. And I think when we came to that, we were still maybe not where we needed to be on inductive methods. But like if we return to this thing, we could prove this carefully now with induction plus the concept of bijection. Like we have all of the necessary theoretical ingredients to go back to that discussion and make it a little bit more rigorous at this point. But not today. So, all right. So then, the Cantor-Schroeder-Bernstein theorem says something that it just seems dumb because the notation is so nice. All right. So this is the CSB theorem right here. CSB theorem. It says that if you have the cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then the cardinality of A is equal to the cardinality of B. Well, this this is very, very nice, right? Because proving the cardinality of one set is less than the cardinality of another simply amounts to finding an injection from one set into the other, and vice versa, right? So put plainly, the CSB theorem says that if we can find an injection from A into B, and if we can find an injection from B into A, then A and B have the same cardinality. Finding injections for my, tricky example over here, finding injections are pretty simple. Like, we can go back to that and use the CSB theorem to prove it pretty simply. Like, let's do it. So you guys tell me, like, I want F a mapping from the closed interval from 0, 1 into 0, 1, an injection. And I also want G a mapping from the open interval from 0, 1 into the closed interval from 0 to 1, an injection. You guys tell me, f of x equals to what? G of x, well, G of x equals to what? It's time to use your formula again, Jacob. How about, oh, x over 2 doesn't quite do it, does it? I was thinking x over 2. What's the problem with that? X over 2 shrinks the closed interval from 0 to a half, right? But we can't hit 0. So what do? Just take this and do what? Add, like, whatever. I don't know. You could add a quarter, maybe. If I do that, it injects the closed interval 0, 1 into the closed interval 1/4 to 3/4, right? And it's in a one-to-one fashion, because if you think about the graph of this function, it's just a line, right? It passes the horizontal line test. You could prove that this is a one-to-one map. It's an injection. How about the other one? Tell me the formula for G.
2x minus a half.
Oh, no, you're thinking too hard.
Oh.
You guys got to know who you are to answer this question. I repeat, you have to know who you are. Yes, it's just the identity. So G of x equals to x will do quite nicely, right? Because 0, 1 is a subset of 0, 1. Man, English really lets us down here, doesn't it? So the closed interval 0, 1 has the open interval 0 to 1 as a proper subset, yeah. Okay, so this means that the number of 0, 1 is less than or equal to the cardinality of open interval 0 to 1. And this means that the number of the open interval 0 to 1 is a subset, less than or equal to the cardinality of the closed interval from 0 to 1. If I have remembered my definition of transfinite arithmetic that I wrote over here, right? A, cardinality of A less than or equal to the cardinality of B if there is an injection from A into B. Yes. So then, okay, so then by the Cantor Schroeder-Bernstein theorem, the cardinality of 0, 1 is equal to the cardinality of the open interval 0 to 1. Yay. Obviously, if you're able to use the CSB theorem, like, this is way, way easier, right? How do you think they proved that theorem? I don't know, but I bet it wasn't that easy. I don't have the proof in front of me or anything, but whatever it is, right? Whatever the proof of this theorem is, it is somehow achieving the implementation of bijections like this implicitly, right? So, like, whatever the proof of that theorem is, it's got to be something relatively ingenious. And anyway, so we'll talk more about cardinality next time. I need to give you back your, and I should collect the take-home part of your test, and I should give you back the in-class part of your test. And if you didn't get the last problem right, I'm sorry about that. I don't think anybody did.